Hello, dear students. The agendas of today's video are to understand what is a wave and various characteristics of the wave through few simple practical demonstrations and carry forward the understanding that will be followed by these demonstrations to go for a more mathematical rigorous formulations of the wave. So let's start with a few demonstrations. I have piled up these dominoes. It took quite an effort to make this final arrangement to create a wave for a few seconds. So these are the dominoes, and what I'm going to do, I'm going to give a little disturbance on this side and let's see what happens. So here I go. Now I'm going to create wave through spring. First a transverse wave and then a longitudinal one. Now let's analyze these little experiments. I've put all the four experiments that I did in just one single frame. In the first demonstration, I gave a very little disturbance here, and now the disturbance is traveling through these dominoes from this hand to this hand. In fact, all the dominoes are following the motion of the first domino, but with a time lag. So in a way, I can say that all the dominoes are copying the motion of the first domino with some time lag. Each dominoes has a limited motion, it just fell down and transfer the momentum to the nearest domino and so on. So through them, the disturbance has traveled, and same thing you can see in case of the transverse pulse. I gave a transverse jerk at the one end like this, and the disturbance is traveling through the spring from one end to other. Initially the disturbance was here, then disturbance reached here, then here and here, and but the each particle was moving in this direction perpendicular to the spring, but the particle while going perpendicular transferred its momentum to the nearest particle. In a way, disturbance traveled from one end to the other, but the particle had a limited motion about their mean position, and the particle more or less is at their respective position. It is oscillating a little bit about mean position, but while doing so, it has transferred its energy momentum to the nearest particle, and thus the disturbance has traveled from one particle to other particle. And to see that this particle is only moving along perpendicular direction, I had this demonstration also. So here you can see that when I given a disturbance to this hand, so all the particles were moving perpendicular to the length of the spring, and that is demonstrated by the motion of this ball, because when this spring hit, the ball moved transverse to the spring. If this end was moving at some angle, so it would have gone something like this or something like that, but it moved like that. So that shows that particles of the medium are moving perpendicular to the direction of the disturbance. And finally, in this demonstration also, what I gave, I just compressed the spring a little bit, so this end moved a little bit towards the other end, and then I bring back my hand, and the same motion that was going on here was followed by all other coils of the spring. The other thing is the reflection back. So what is a wave motion? In all these previous demonstration, we saw that the disturbance is traveling through the particles, but particles themselves are not moving as a whole. They have a limited motion, and in their limited motion, they are transferring energy momentum to the next particle, and thus energy is transferred from one place to another place without the bulk motion of the particles of the medium. So we can say that wave motion is the transfer of energy and momentum from one point of the medium to another point without actual transport of matter between the 2 points. Then we saw two different types of wave. So first thing is the wave transverse wave. What is transverse wave? uh, we saw that the disturbance was traveling along the length, so this is the direction of motion of the disturbance, and particles of the medium were moving perpendicular to the direction of the disturbance. So a wave motion in which particles of the medium move perpendicular to the direction of motion of the disturbance is called transverse wave. And then we also created a longitudinal wave. In longitudinal wave, this was the direction of the disturbance. It was traveling through the this whole spring along the length, and the medium particles of the medium were also traveling along the length. So a longitudinal wave is a wave in which particles of the medium move along the direction of the motion of the disturbance. Then what are the variables in a wave motion? And right now I'm taking a transverse wave. So the variables of in transverse wave are, suppose this is the medium, that is I have taken the slinky. It could be string. So the particles of the medium are along say x-axis. So one variable is the location of each particle. So it could be some x here. So one variable is the location of each particle, equilibrium position of the particle of the medium, and other variable is the direction along individual particles are moving. So that is a y direction here. So each particle, right now this particle has come from here to here. Similarly, when the pulse will reach here, this particle will move along here to here. So another variable is the displacement y of a particle of the medium, and of course in a wave motion this x and y varies with t. So we have another variable time. Now, what is a wave motion? Wave equation, 1D transverse wave. For a 1D transverse wave, we saw that just in the previous slide that in wave motion there are three variables x, y, and t. X is the location of the particles of the medium, y is the direction along which particles of the medium are moving, and t is time. So a wave equation is an equation which enables us to tell the motion of each particle at any time. So if I know the displacement of particle at any location at any time, so it means I know the wave equation. So wave equation, in the wave equation there are three variable. So if I know y as a function of x and time, so that is a wave equation. How we can find a wave equation? There are two ways we can find a wave equation. If a snapshot of a wave is given at certain moment and a wave velocity is known, so if we know the snapshot at certain moment, like suppose this is a snapshot and the wave is moving like this, so we can tell, knowing the snapshot at a moment and wave velocity, we can tell motion of each particle of the medium at any time. So that is a wave equation. And also the wave equation can be obtained if we know vibration at certain point and wave velocity. So by knowing the exact motion of one point, if we fix one point, that is called the motion of that particle is called the vibration. And at the same time, if we know the wave velocity, so we can find the wave equation also. So by these two we can find wave equation. So now let's do some mathematical part. So we want to write a general equation of a 1D wave. I have selected a transverse wave. What is given? that a wave is traveling along positive direction with the speed v. Particles of the medium are moving along y direction. So this is a transverse wave. And a photo of the wave, that is a snapshot. It could be of any form. So I have given written a general form. The snapshot at t is equal to 0 is here what is time is fixed. So snapshot just is a waveform that is a function of y and x. So that shape is gx. Y as a function of x is gx, and it's like this. Suppose these are x axis along the which medium is there, and wave is traveling along x axis. This is y axis, and this is a snapshot at t is equal to 0, and a wave is traveling along positive x direction with velocity v like this. And if we have to find wave equation, we should know what is the value of y as a function of x and t. So this is a general position x, and the wave has reached to the general position x at general time t, and we have to find y as a function of xt. You can think like this is a train is traveling with velocity v, and I can give some values here to illustrate this. Suppose there are two stations A and B. Train started from station A at t is equal to 0 and reached to station B at say t is equal to after say 2 hours. The position of station B is say 100 kilometer, and train was traveling with a constant velocity say 20 kilometer per hour. So can we tell that what was the position of A? We see that time interval between arriving of train from A to B is 2 hours. Train was traveling with a velocity 20 kilometer per hour. So the separation between the two stations should be 20 into 2, that is a 40 kilometer. So if the position of B is 100, so position of A should be x is equal to 100 minus 40, so that should be 60 kilometer. The motion of this wave pulse is same as the motion of the train. The wave pulse has arrived at position x at time t. So we have to find that at t is equal to 0, what was the position of the pulse? Because it is traveling with velocity v and the time interval between the two positions is t, so the distance between the two positions will be vt. So if this position is x, so this position will be vt less than that, so that this position will be what, x is equal to x minus vt. So what we can say that the disturbance at position x at time t is same as disturbance at position x minus vt at time t is equal to 0. Why is so? Because each particle of the medium copies the motion of the other particle with a time lag. So whatever disturbance was here, that has that the same disturbance has arrived here. So I can write y as a function of xt. Displacement at position y at time t is same as displacement at t is equal to 0 at the location of x minus vt. And what is given? Y x at t is equal to 0 is g of x. Here t is 0, that is fixed here also. So as we know that if this is g of x, and now in place of x if I have put x minus vt, so this answer will become yxt is equal to g of x minus vt. And this is the general equation of the wave given a snapshot is given and the wave velocity is given. And here we are assuming that wave is moving along the positive x direction. If wave is moving along negative x direction, the sign of a bit inside this bracket x minus vt will change, and that will become g of x plus vt. Another way to write equation of the wave is if we know the equation of a vibration at a point and wave velocity. So what is given now? Again, wave is traveling along positive x direction with speed v, and particles of the medium moving along y direction, and a vibration at x equal to 0 is y x equal to 0 t, that is a sum function of t. So we know only the motion of one particle that is a x equal to 0 as a function of time. That could be a SHM or any other kind of a motion. So we have to find the equation of the wave same way. Suppose this is our x-axis, the medium, y-axis along the which particles are moving, and this is a pulse. This pulse is moving towards right direction with velocity v, like this. And at what we are known that how it is vibrating at x equal to 0, and so we have to find what will be the value of y at position x at time t. So that is what we have to find. So now we have the two position. This is the position x and this is the position x equal to 0. The separation between these two position is x. The wave that is at position x is at time t. So what will the time interval between the wave to travel from this position to this position, because it is moving with a constant velocity v, distance between them is x. So time interval for the wave to go for 1 to 2 would be x by v. So if the wave is at position 2 at time t, so the wave would be at time t minus x by v at position x equal to 0. So now we can write the value of y at position x time t is same as the value of y at position x equal to 0 at time t minus x by v, and y at x equal to 0 at time t is f of t. Now in place of t, if this has become t minus x by v has become, so yxt will simply become f of t minus x by v, and that is the equation of a wave if a vibration at a point is given and the wave velocity is given. Likewise also, if the wave was moving along negative x direction, then this equation would have taken the form yxt is equal to ft plus x by v. So this is all for this video.